Yeah, thank you. I'm guessing right, Michael. So I had the great pleasure to give the first seminar in this KITP program and introduce you a little bit to the work that we do in New Zealand on pyroclastic density currents by measuring into active flows and doing large-scale experiments. In that seminar, I was showing you perhaps the first direct measurements inside pyroclastic density currents that I was combining with large-scale, or that we were combining with large-scale experimental data to come to the conclusion that a lot of the dynamics of pyroclastic density currents and their hazards are strongly associated with turbulent fluctuations and energy focusing into large-scale coherent structures and into gravity waves. Now, that conclusion and the presentation of these results of measuring into flows might have given you a wrong impression, or at least to those of you who are not from the volcano community, that we would have a lot of quantitative data into these currents, but we don't. What we actually do know best, and where most of our data and interpretations come from, are what's been left behind the deposits of pyroclastic density currents. And so in this talk, I would like to focus more on these deposits. For probably the last half a century or so, volcanologists have recognized that there are two main different types of pyroclastic density currents deposits, or end-member type of deposits. Here's one of them: massive deposits that, in analogy to fluvial systems, volcanologists interpret or assume that they are the deposit of a dense granular fluid flow. By contrast, we observe deposits that are strongly bedded, cross-bedded, sometimes dune-bedded, and we assume this again in analogy to fluvial analog systems, because we cannot look into pyroclastic density currents, that they are deposited strongly by traction of a fully dilute, fully turbulent flow. And so with the recognition of these end-member types of deposits, the things that we can really observe and measure, and where a lot of data has accumulated over centuries of work, a lot of the experimental and theoretical work was going on to studying these end members, fully dilute systems and fully dense systems. But over the last 10, 15 years, and strongly triggered by some of the translation of work of the multiphase physics community into volcanology, and George was making this point that perhaps 20 years ago, he and Ellen Burgess sort of really helped to push that translation. There's a whole world of particle concentrations that must occur in pyroclastic density currents, where very different behaviors from just fully dilute and fully dense systems occur. So the work that I want to present, I would like to acknowledge here some of the stuff that I've learned from co-workers that are all involved in the large-scale experimental work that we do at Massey University. Before, I'd like to show you a little bit of some of the stuff that we've learned from deposits. And I'll take you here out to New Zealand. You're here in the Tongariro National Park, and you're looking here at two volcanoes, the Lower and Upper Tamari volcanoes. These are volcanic systems that were believed to be dormant. There's a photograph being taken of the Upper Tamari and Lower Tamari craters, where the Upper Tamari crater hadn't seen an eruption in 120 years. Now, in 2012, an eruption occurred, and a new vent opened up, a roughly 350-meter long fissure, and out of this, through unloading of a pressurized system, directed pyroclastic density currents spread out to the east and to the west. So that depressurization was caused by a failure of the volcanic edifice and the production of a debris avalanche that produced an eruption column that spread volcanic ash up into the Pacific, and ballistic hazards occurred. However, in addition to those volcanic hazards, we observed another phenomenon. I'll just show you some of these features. We observed the loading of ash onto vertical surfaces, which suggests a lateral emplacement of a current that in this case also was wet. We've seen that up to 1.6 kilometers from source, trees were knocked down, and even closer to source, we saw these fields of dune-bedded deposits. So if volcanologists look at these features, they immediately recognize that we're dealing with pyroclastic density current deposits. And that was a bit of a scary moment for volcanologists in New Zealand, because we hadn't dealt with pyroclastic density currents for quite a few years, in this case in a national park that is highly frequented. This was not any type of pyroclastic density current, but a pyroclastic density current that's particular energetic that we call a directed blast. In this case, this fissure here in white blasted out to the west and to the east before an eruption column also occurred to the main crater. You see here the directionality of these deposits, and you see contours of equal thickness of the deposit that spread out mostly to the west and to the east in this case. Just point out here that this is perhaps one of the most scenic walking trails in the world, and one of the most frequently ones in New Zealand, the Tongariro crossing that was overrun by these pyroclastic density currents. It's an area that is extremely important for the tourist industry in New Zealand, and it's very close to the main hydropower schemes that power a large part of the electricity demand for the North Island of New Zealand. And it's very close to the largest river, and ash falling into the river will affect the drinking quality, and a lot of this water is used by one of our largest cities, Auckland. Importantly, this pyroclastic density current was extremely small. Only 380,000 cubic meter is the size of the volume of the deposit, but the quality of the deposit was extremely nice. Sorry. Yeah. Oh. And I want to show you here some of the characteristics of these blast-like PDC deposits, very close to source or to the vent. We do recognize these in a lot of these very energetic blast-like deposits that it's been consistent of a tripartite structure. The lowermost part is a massive poorly sorted part, sometimes we call this part A, which is overlain often erosively by a cross-bedded, dune-bedded part B, and a very fine ash dusting with lapilli on top as part C. As we move out, yes?
What are the cylinders that I see beneath the
What is this?
Yeah.
That's a tool that volcanologists use to shave off outcrops and make it clean. So, it comes from Japan, where they use it as a gardening tool.
How big is it?
Exactly that size. Going further out, you see that same structure in there. You see a very strong erosive surface to the soil. This massive poorly sorted layer, A sitting below a next layer, which are these stratified dune-bedded deposits, and that's overlain by a fine dusting of ash on top of this. And we can follow this stratigraphy through to source. We are here at 1.6, 1.7 kilometers from source. The deposits are strongly dune-bedded. Further, they become more undulating or planar, but show exactly the same structure, and only close to the very final runout of these flows do we lose this more coarse-grained, poorly sorted layer at the base, and these deposits are extremely thin. You see here the tip of a knife for scale to recognize these upper two units. Now, we did a few experiments to try to understand how we can understand the formation of these deposits. We do this, and some of you have seen this before in a large experimental facility. There's a hopper where we put in volcanic material, we heat it, discharge it by opening the hopper. It's diluting during free fall and producing a gravity current that's then running out for 35 meters. We use natural volcanic material from a previously erupted pyroclastic density current. It's roughly 2,000 years old. Mine this from the field, pre-screen it to sizes smaller than 16 millimeters. This is inside this facility where there's a large hopper structure that has a heating element inside to heat the material, and there's a chute underneath. So the material gets loaded into the hopper, bucket by bucket. It heats over several days, and then the mixture is discharged into the channel. This is what it looks like. We do take measurements of velocity, temperature, density inside these currents in vertical profiles throughout the outrun of these currents. We look at how topography is influencing the propagation of these structures. And here you see this natural cliff that is, for the largest flows is blocking the flows, but not some of the students. Now, I'm actually here showing data from this benchmark experiment that Joe was mentioning. Right? So this is a relatively dilute flow. You see here data of the bulk current density over time after the impact with the channel. You see that this is a mixture that is strongly non-Boussinesque, and it's diluting due to the sedimentation of particles as it's running out. You see here data points of the volume of deposit that's being created at the base of the current. You see this strong anti-correlation of particles forming a deposit and the flow diluting. And understanding this relationship is very important for building hazard models to see how the Froude number that is driving, or the density contrast that is driving the flow is evolving. Here images of the flow front as it's propagating over time, and at the same time steps you see at a very different scale the shape of the deposit, how this is building up and it's growing out outwards and upwards as the current progresses. You see that you're dealing with a relatively shallow flow of 2 to 3 meters that finally is strongly entraining. When pressure drag becomes important, the current becomes positively buoyant and lifts off at the end of the experiment. An important feature that we saw in these dilute pyroclastic density current experiments is that the experimental deposits in their sequence from proximal to medial to distal reaches are very similar to these natural deposits that we see in deposits of Mount St. Helens, the Tamari eruption in New Zealand, and in other eruptions that we studied in Indonesia, for instance. This tripartite structure of this massive units, or sometimes vaguely stratified massive units, being overlined by stratified deposits and the fine ash dusting occurring at the very top. Now here is a video of some of the processes, I hope, that occur close to the base of these flows. So you see the progression of the head of the flow and the sedimentation of clustered structures that are moving strongly downwards. They're displacing air and causing a lot of turbulence. These lead to the deposition of a very mobile granular flow at the base of the flow. So rather than tractional deposition, this rapid deposition of clusters is actually forming a very mobile granular fluid underflow. It's only towards the end of the flow, we also see some dune and antidune features that form in here, only towards the end of the flow, when the flow is very dilute, is tractional deposition taking over, which is believed at the moment to cause these massive and stratified flow deposits. So true tractional deposition is actually only causing a very small fraction of the deposit that builds in here. In the seminar talk, I was largely focusing on the low frequency oscillation of density and velocity that we observe in these flows. That's illustrated here again as the downstream velocity in these flows. Right, so you see these oscillations that occur at roughly 800 millisecond intervals, and that's linked to the large-scale coherent turbulence structures. If we look at the vertical velocity component of the flow, you see a different pattern. There are these stripes that you see of high and low vertical velocities. Red colors indicate a strong downward velocity in here. And the frequency of these high velocity raining of particles is at a much higher frequency than these coherent structures that occur. They occur at roughly a period of 150 milliseconds. But they are very periodic, this raining out of particles. Now we believe that this is due to the sedimentation of mesoscale clusters. What you see up here is a plot of the turbulent fluctuations measured at a static observable location. You see a height time plot of turbulent fluctuations. And we do see these large-scale coherent structures that I've talked about in the seminar. They are also visible here on these plots for the head, the body, and the tail of the flow, if you like, being illustrated here in vertical plots of turbulence and intensity. So very strong turbulence intensity associated with the bypassing of the large-scale coherent structures. Now these currents are strongly vertically density stratified. You see here profiles of the volume concentration in these 3 example parts of the flow. All right. Now in this situation, we would expect that the high density at the base and the strong stratification would dampen turbulence. And you see here calculations of the Richardson gradient number, which we can sort of use to test how stable this stratification is. What's surprising is that the turbulence intensity at the base of the flow is actually not low, but it's actually quite high. Despite the fact that the Richardson gradient number is extremely high. This axis here is actually broken, as you see, and we have extremely strong and very stable density stratification. So what's inducing that strong turbulence at the base? We believe this occurs to the settling of mesoscale clusters. What you see here is a snapshot of the vertical velocities throughout the flows, and you see these high velocity, vertical velocity regions neighbored by low velocity regions, and they actually are associated with falling, fast settling mesoscale clusters that reach velocities that are higher by a factor of 2.5 than the typical grain size of the neighboring flows. Eric did a few simulations of this kind of situations to show that in this case of very rapid settling of mesoscale clusters, pore pressure can be created. Here's another picture of these mesoscale clusters sedimenting down to the base and how they're displacing ash poor or gas-rich regions, which rather move upwards, which we believe is causing this local turbulence. In our experiments, this is causing a particular zonation at the base of the flow. So you see in here a region that I've called T, called the transient region. This is where these mesoscales start to sediment into, and that because the sedimentation of mesoscale clusters is strongly periodic in time, that region is also moving up and down, and it's sedimenting into a bedload region. This is that region that can cause these very fluid-like, wave-like granular fluid waves to occur. We've measured the thickness of these mesoscale clusters with distance, and something that I do find quite surprising. See here histograms of the frequency thickness distribution of the histograms close to source, intermediate, and distal regions, is that the thickness of these mesoscale clusters is increasing. At the same time, we were lucky to sort of probe the grain size distribution for 3 of these mesoscale clusters. We see that they're becoming coarser grained, finer grained, and better sorted with distance, much like the surrounding flow that they sediment out from. Of individual mesoscale clusters, all right? We would love to measure their lengths also to get some relations to this, but we haven't been successful to do this yet. This is another picture of the sedimentation of these mesoscale clusters as it's forming this transient regions that is sedimenting out, in this case, a bedload region, which is not a tractional zone of individual particles, but rather these fluid-like granular fluid waves that move out for decimeters to meters into
Gert, in these images, is light color high concentration or low concentration?
High. Sorry, yeah. So this is a quite busy plot, so try me to recall what this all means. You see here the flow passing at a static observer location where we try to work out what types of deposits are forming, what the deposition rate is that occurs underneath these flows. I've also marked out in here the thickness of these transient regions where these turbulent mesoscale clusters sediment into, the thickness of the bedload region, and you see here the thickness of the deposit that forms underneath. You see that during the passage of the head, there is no deposition or no net deposition that occurs. And you see here how this transient region is moving up and down due to this feeding of this fast settling structures periodically, roughly every 150, 200 milliseconds or so. At a certain amount, after the head, they start to form a deposit from these thick granular fluid waves, or shifting waves, as we called them previously, and they are associated with very high deposition rates. So they form these massive units that we see as unit A's in deposits. A little time later, we see an alternation between these shifting sand waves that come from the sedimentation of these mesoscale clusters and tractional transport, and they seem to form a combination of stratified and laminated beds that we see as these unit B layers in field deposits, and much later, when the flow is much less concentrated, to be formed laminated topping of the flows that occur at the end of the deposition. So you see in summary these processes that occur again. See in light colors high concentration particle settling that occur, the bypassing of the current here, formation of these granular fluid underflows, alternating granular fluid underflows, and tractional deposition that's producing stratified beds, and only much later purely tractional deposition that is forming a fine dusting towards the end of the experiment and producing that structure that we see also in natural deposits. Now we are wondering how important are these clustering processes for natural pyroclastic density currents. We first want to see sort of, are they dominant for the entire round of our experiments? So we've used these graphs that Ellen Bergeser and George Bergans were suggesting to the volcano community to map out these different regions of gas particle feedback in pyroclastic density currents that are defined by the Stokes number and the stability number. Important, and in lots of models, we assume that we can model a pyroclastic density current as a homogeneous, fully dilute as a suspension of particles. 3 years back, Eric and I, we've mapped out for a single scenario or a single time shot, sort of where pyroclastic density currents in our experiment sit. We figured out that the head and the body region, they are actually sitting in regions of very strong feedbacks, where particle might either form mesoscale clusters up in here, or where particles tend to migrate to the peripheries of eddies, unroll and might cluster. And it's only the wake region, the region that sits on top of the pyroclastic density current, that is actually fully homogeneous. In these newer benchmark experiments, we've mapped these Stokes stability numbers through different force regimes throughout the current. They're characterized by 4 different regions. The first one is a strongly inertial regime where strong deceleration occurs. The second one is an inertial buoyancy regime. In the third regime, inertia is balanced by pressure drag forces. And this is the last regime when the buoyancy reversal occurs. And you see here different time steps of these diagrams of Stokes and stability numbers throughout these 4 regimes of propagation. Important is that we do see these very strong couplings for most of the round of the flow, and it's only in the very late round and towards the buoyant liftoff that we do see a very homogeneous suspension of particles. So you probably need to care about these clustering effects when we model flows. This is just a graphical illustration of the flow advancing and the head, body, and wake parts as they are progressing outwards, where these differently gas particle feedback mechanisms occur. And again, you see that regime of fully homogeneous transport, that regime 4 in here, only occurs very late stage. But for most of the run-out distance, at least in our experiments, these feedback mechanisms are extremely important. So in summary, we observe in our experiments that mesoscale clustering, or the clustering of particles, occurs at particle volume concentrations as low as 10 to the minus 2.6. This is quite a bit lower than clustering that has been observed in monodisperse experimental systems, and could very well be that it's due to the very large grain size distribution that occurs in our systems. The fast settling of clusters is inducing turbulence in the lower part of the flow, despite a very stable stratified flow environment. And the sedimentation of these clusters is producing mobile granular fluid flows that deposit massive beds that we do recognize in natural deposits. And in alternation of this process with fractional bed load, we can produce stratified beds. So previously, mechanisms that are borrowed from concepts from fluvial systems that dilute pyroclastic density currents deposit by purely traction are perhaps not correct. And that's it.
Kimberly and Michelle.
Thanks, really fascinating talk. I have a question about the clustering again. Would you mind going back to the slide where you show the evolution of the cluster size distribution? Yep. So part of my question involves something you said at the very beginning, which was that the deposits seem to look poorly sorted. And then we have this, okay, so it's time, when it says clusters thicken with distance, can you, is it later, is it like going from top to bottom, is it later in the,
yeah, you see here measurements of the cluster thickness and cluster grain size distribution for one case at 3 different profiles, very close to the source 10 meters and at 15 meters
From the front, is that what you mean by the source?
from the point where it impacts into the channel.
Oh, and the channel is this gaseous channel, right?
Yeah.
Okay.
That's exactly right. These positions, we measure the bypassing frequency and sizes of these clusters.
And
what this means, why they are thickening, to me it's a little bit counterintuitive. I'm not quite sure. And so it's perhaps important to look at how their length is changing with distance.
so is this, I'm sorry to repeat myself from before, but it was going so fast. Is the thickness of the layer?
Nope. The mesosphere clusters before they sediment downwards.
Oh, up there is the thickness of them, and then you sort of, and then at some point they become grains and they move in bedload.
Exactly.
Okay, and then, so linking to something, this is great, thank you very much. And then the other question is linking this to, it looks like you get the largest clusters at the bottom and they kind of move along and.
Yeah, I would agree.
But at the beginning of the talk, you said there's sort of poorly sorted deposits.
Yeah.
And why don't you see segregation in the deposits? And it seems, in like preferential ordering of the different size grains. And here it seems like you have a layer of large grains, or is it just, this is dynamic, that's the static, and there's something in the middle we don't understand?
Not quite sure I understand the question, right? So these clusters are very fast settling flows that sample whatever is clustering. And they form like a fluffy intermediate concentration zone that is just collapsing and forming granular fluid flows. So there's a quite poorly sorted mixture that is collapsing into the bed load, and due to its very rapid deposition, these wave-like granular fluid flows are created.
I think that answers my question. Thank you so much.
Appreciate your talk, learn a lot. Could you go back to the Stokes and stability number slide? So I think I understood where the Stokes came from. You basically have UT over G. UT is the terminal velocity G, so that's how the Stokes.
That's the eddy rotation velocity. That's the diameter of the eddy, and that's just gravity. And here again, there's the terminal fall velocity of the particle sizes, and that's the eddy diameter. So what you see in here that are lines plotted, and they are, so the points sit exactly at the median grain size diameter, and these lines sort of capture the 15th and 84th percentile of the grain size distribution of particles in different regions of the flow.
Forgive me, I'm still totally confused. So UT is the terminal velocity. What is delta UI?
So we directly measure the eddy rotation velocities, and we directly and we determine the terminal fall velocity theoretically by looking at the grain size distribution in the flow, because we do measure the flow grain size distribution as a function of height and time.
What would that measure stability? What would that be a measure of stability? What do you call it that way?
I don't call it that way. George might be able to answer this. These are basically two different time scales, right? So one is basically describing the coupling of the particles to the turbulent flow. The other one is a time scale of the residence time within large-scale structures.
I see. Yeah. Okay. Now, a quick comment. I think you mentioned that you were surprised by having solid volume fractions that were on the order of 0.1%. You said 10 to the minus 2 point something. It's rather common in circulating fluidization and pneumatic transport.
To have clustering.
To have clusters, yeah, they're full of clusters, and they. Yeah. So to me, it's not the number that surprises.
Well, I thought that currently the assumed limit for clustering on-site is sitting at 10 to the minus 2. So we're almost sort of going no.
I did work on circulating fluidization early in my career, and I can assure you that much smaller volume fractions in those units.
Well, that's important to know, right? So which shows even more how important that process will be at extremely low concentrations in our currents as well. Yeah.
Eckert, I think that we got these ideas from you. That paper you wrote a long time ago, Vasual Myberg, you had a form of the stability factor in there, I believe, and Alon and I. So you're sitting there quietly thinking, hey guys, I want to give you a shout out because I think we have benefited so much from your intellectual leadership. And this is another example of that.
I have a technical question. How do you measure particle concentration?
Yeah, so this is actually a technical
should be optically opaque.
issue. We tried with different approaches, and I hope we get better and better. We started with optical approaches, and we had more high-speed cameras that became a problem because of some thermal problems of the radiation. We do have probes where that are probes that let the flow in and the gas as well, but only the gas can escape there. We can see the volume is changing, and we use the velocimetry in front of the camera to calculate concentration. A much more detailed method to do this, and that's where we've changed to now, is to use a combination of pitot tubes and dynamic pressure sensors. So these are pitot tubes that we've self-built by using the needles that you use for veins, right? And so what we figured out that in this case, in our flows, if they don't block, then they actually measure the gas velocity through Bernoulli rather than the full continuum pressure, while the dynamic pressure sensors are measuring the dynamic pressure. So in combination, we can use these dynamic pressure and fluid velocity or gas velocity measurements to compute theoretically density, which seems to be our most robust way of measuring density at the moment. And also in regions, Michael, where the flow is unconfined and we cannot look inside. And so, yeah, but it's not easy to get good measurements of density.
And maybe one last quick question. In the previous talk, Joe Dufek talked about shock waves. In the field deposits, I would guess that the New Zealand example you showed us probably generated shock waves. Is there anything we can recognize in a deposit that would be diagnostic of something like a shock?
Not directly. So in this case, we approximated, and I think Eric did quite a bit of work on the ballistics associated with the eruption, that we had velocities in the order of 120 meters per second due to the overpressurization of the system. And these pressure waves were recognized by infrasound sensors. We do recognize a very different structure of the deposits in the proximal region, where the flow is strongly expanding. Very coarse particles fall out before it transitions into a full gravity current deposit. That's probably the most direct observation of a overpressured system that is migrating into a gravity current deposit. I don't think that we have from deposits any evidence on shocks as far as I know.
So let's thank Gert once again.